so our next speaker will be Sebastian, talking about, I guess, 3D engineering.
Okay, hi. So I'm Sebastian. I'm working at Kernel Labs, and I have been doing this for the last almost 10 years. So in the summer, like 2 years ago, we got a little project funded where we were able to look into 3D acceleration with a view on GPU virtualization. And so since we're at Kernel Labs, we decided to have a deeper look in it and try to get something working on our microkernel component-based system. Hence the very complicated title. I maybe should have called it 3D acceleration on microkernels. So short outline, as usual, short motivation, then I try to explain what parts do we have on a GPU that needs to be multiplexed and shared by multiple clients, how we do it in user space or in keynotes especially, and then I'll just the results. So it's going to be a pretty straightforward talk. Come in, please. So, like Tim Sweeney says, during the last 20 years or something, GPUs have become more and more important and way bigger. Like they used to be very small, very slow, but in the future it may even look like this. So this would be an Intel Skylake core with integrated Intel graphics. If you just look at it, you see that's the GPU, and that's your quad-core processor. So maybe these things are kind of important, and since your browser and everything now uses this thing, like multiple applications will use it, you probably should take care of it. So another thing is GPUs have become really programmable. So in the past you would say, okay, draw these polygons, draw these vertices or something like this, and now you have something called shader languages. So you can have this code, the driver will compile it at runtime into GPU machine instruction set code, and this can produce something like this. So this was taken from Shader Toy. And this is executed by a browser, right? This is a browser application. You can write your shader, compile it, and it will be there. So this would be some disassembly of the code that's generated. So it kind of looks like x86-ish, like with vector stuff and this kind of things. So one idea we had, maybe we should treat GPUs a little in the way like we do, let's say, CPUs or virtual CPUs or something like this. So, okay, can you hear me actually? So should I try to talk a little louder? So I have a very low voice, so that's very hard. Okay, so that was the motivation. And what we did next, we just had a look into a modern graphics stack on Linux. So what does it look like? So some people might be familiar with it. On top you have your 3D application, and then you need some sort of 3D library. Let's say OpenGL. So Mesa supports OpenGL, and OpenGL consists of one or more layers depending on what you want to do. There's one on the left side you see the embedded GL. That's the integration into the windowing system. There you say, okay, OpenGL use this window, use this surface, and here's your frame buffer and things like this. You say, what's the bit depth and all these kinds of things. Then you have your natural OpenGL layer, the application programs against, and a backend called the direct random infrastructure. So, and here you have, for example, an Intel backend and a software rendering backend. And of course, the Intel backend will eventually talk to the kernel driver and render the graphics. But the first thing we did, we had a look at this whole thing, to evaluate the complexity of this. So we looked it up and just tried to identify the parts which are important if I wanted to support an Intel graphics cards. And you can see the whole Mesa stuff roughly consumes 300K lines of code, including a shader compiler. So it's highly complex. And you really don't know what they do. So you don't really know how they translate shader language in what instructions on a GPU, because this stuff is not really documented that well. And then, of course, we will talk about this later because that's the main point, the kernel driver, which actually schedules the generated code onto the CPU, onto the GPU. So, but first, we try to get this Mesa thing working on our Kernel system just as a proof of concept. So we said, how hard could this be? And we don't want to use the Intel stuff yet. We want to use the software renderer first. So we kind of ported it over to Keynote. And how this usually goes is you see a lot like pictures like this. So you just work further and you see things like that. And eventually you see your demo, standard Gears demo, in software render. So after this, we decided, okay, let's follow the actual GPU path, which requires enabling the Intel backend for the direct rendering interface. And then you have this library called the Direct Rendering Manager. And this library directly talks to the kernel. That's the kernel interface. And sends jobs to GPU. So basically what this library does is it tells the kernel driver, give me some memory from the GPU, give me some, they call it buffer objects, where you can store your image data and your vertex data. And this driver fills it with compiled code, with image data, with vertex data, sends it to the kernel, and the kernel will execute it. So the big question arises, how does the kernel GPU driver part actually multiplex stuff? So, because what you want to have is, if you have multiple clients in user end, you want to kind of separate them so they cannot cross-talk or anything. So we looked at the kernel driver and we saw a lot of outdated code, like for older Intel graphics devices, and features we didn't really want to support. And this is why the 100,000 lines of code is like not fair comparison, because we just wanted to do the new software GPU generations. And we just wanted to take advantage of new features. So the question arose, is this feasible and how complex is this? So next I'm going to talk about the things you actually want to multiplex and the features we found that we want to use. So that's going to be a little bit more technical, but you don't really have to understand it, but I kind of will give you an idea. So this is how Linux does the multiplexing. Here are two clients, and Linux multiplexes through the DRM library. So you have a DRM context in the kernel for each client, and the client tries to identify the context and separate it accordingly. So let's see here. Okay, so in the GPU, you have like one or more engines. They call it engines. The most important one is the render engine. This is the engine where you send your 3D operations and your general purpose GPU processing stuff. The next important one is the splitter engine. This is meant to copy, like very fast, copying pixel data from one buffer to another. And then you have some nice to have things like video decoding support or something. Since we wanted to concentrate on 3D, we just looked at the render engine in our scenario. Okay, so now it really gets more technical. So basically, here you have your GPU. There you have the render engine. And the only way for the CPU to actually access the graphics memory is through a so-called aperture. An aperture is some MMIO window, so memory MMIO window in your memory. And the CPU has to map this memory through the aperture. And this is done, I will come to this, through a thing called the global GTT, the global graphics translation table. So of course, like in real CPUs, GPUs have like page tables. So there are all ones called the per process page tables, and we will come to this next. So you can see the render engine actually can access both page tables, but mapping of graphics memory only goes through the aperture. Okay, here we go. So every graphics card has this global graphics translation table, and there's just one, and it's shared by all GPU clients. So if you want to map something through there, like through the aperture, it has been handled by the GPU driver in kernel. So he has to make sure that there's no cross-talking or whatever. On the other hand, you can say, okay, each client can have a per process page table, and this one is hierarchical, like we know it from x86 CPUs, and can be associated to a client. That's the important thing. So the format of whatever, it doesn't really matter for us now. So then what you actually really have to share is the aperture, because it's limited. So if you want to like map your image through the aperture, you have to make sure each client only sees his things in the page table. And there's like almost minor thing, it's called fencing, because the GPU doesn't store like image data linear in the memory. It just tiles it and stores it non-linear. So you can like detile and tile it through the fancy registers. You just say something like, okay, this region is X-tiled, and the GPU will do the rest for you. But these things are also limited. There are only 32 registers, and with multiple clients, you somehow have to share it, either by like doing partitions or dynamically assigning it to clients. So these are the most important parts you actually have to share. And the other thing is the rendering has some sort of command buffer. It's a ring, and there you can write GPU commands to. Like, let's say something, a batch buffer is like a buffer containing GPU commands, and you say, okay, execute this buffer. And in the past, all the clients shared this hardware ring. So this has changed too. So in the past, you had this hardware ring, you would write your commands in there, and there was a head and a tail pointer, and you would say, okay, GPU, new head pointer, and GPU would execute it until it reached the tail pointer. So now, in newer GPUs, they have this notion of exact lists, and maybe the best comparison of an exact list is something like, if you're familiar with VTX, they have this VMCS area where they store the whole machine state, and this is kind of comparable. So you have per client, you have this exact list, and in there is a page table pointer. There's like the ring, the client with the commands the client wants to execute. There's a hardware context where the GPU stores, like if you like preempt the context, the GPU stores this whole state in there. And there's a hardware status page where you can say, okay, what's the state of the GPU? So you can have this per client, and the only thing you do now is, all right, let's write our commands to the logical ring, set the page table, and then say to the GPU, okay, execute it. And the GPU will switch the page table, copy the logical ring on the real hardware execution buffer, and you're basically done. So you have to make sure that there's an interrupt or something in there, because what you still can do is you can say something like, okay, I have a shader with an endless loop. So you're not, you cannot do anything about it. The only thing you can do, can have a watchdog timer that says, if the GPU doesn't come back because of some malicious attack, you have to reset it. So that's the only thing you can do at a time. Okay, so now this is kind of what I just explained, and how we did it on GNet is we say on GNet we have this notion of sessions. So you have like your GPU multiplexer in user space, so not on hardware, but in kernel space. And you have this session interface where a client can say, okay, I want to have a GPU session, and the multiplexer will allocate all the necessary resources for you, and you can like submit your command buffers like you would do in DRM, just in user land, and through a different kind of session. So here you have like n clients, and this is the information every client has to, be provided. So, and as I said, you have to slice the fences and the aperture. There's a page table per client and a hardware context. Okay. So this would be like putting this in the Mesa context we had before. So we still have our 3D application. We say this whole Mesa thing is for us is way too complex and way too large. So we link it into the client application, and we exchange the DRM library backend, so it will talk our GPU session talk. So, and establish a GPU session to the GPU component, and you basically have a user level component with a component driver which cannot crash the kernel at all. Okay, we start the porting again. Writing the multiplexer again. This time you could have seen something, and the gears were there for like a second, then they were gone. Turned out we didn't do the synchronization well, so the rendering wasn't done, and we already painted the picture. So most of the time you get like portions of it or nothing. This is what tiling looks like. So if you don't detail anything, you always get these nice lines there. So then you know you did something wrong. And the other thing that's really hard to do is when writing something like this, I mean, they got pretty good documentation into like 10 volumes or something, but you cannot do without the Linux driver because there's so much missing, so many little details. So then have you flush, I'm almost done. So then have you flush the cache, or, you know, so this little, there are croaks for some devices. So this took us a long time to actually achieve. So in the end, we ended up with a demo scenario like this. So this would be a G-Node demonstration component system. It's a very small one. So you got your root task here. It launches our GPU multiplexer slash 3D renderer. This is not really necessary, but just for demonstration. Then we have our frame buffer, must come from somewhere right now, like our real hardware frame buffer, and our nitpicker GUI multiplexer. So in the launcher, this would be one 3D subsystem. And we'll start a 3D application. And we have this nit frame buffer which connects to our GUI server. It gets a frame buffer session, and so the multiplexer in the session will render an offline picture into the 3D application, and the application will copy it to the nit frame buffer, and the frame buffer will multiplex it on screen. So you can have multiple applications on one screen. Okay, results are very shortly. So we are actually pretty proud that we were able to write this whole multiplexer in 10,000 lines of code, but this is just Broadwell. So for the Skylake and Kaby Lake, you will have to do some more stuff. For Skylake, for example, you have to load microcode again. It's the new trend at Intel, microcode for anything, even Wi-Fi. So, and the whole trusted computing base really gets smaller. So we were not able to add the Mesa library to the trusted computer base because it's too complex and way too large. Okay. So current state, we are supporting Mesa for Broadwell GPUs. In the next step, we're going to take advantage of the Blitter engine, so we can copy pixel data very quickly. We do it in software right now. As I said, Skylake, Kaby Lake support would be nice, and maybe we look into a GPU virtualization, but we don't know because Intel has something called they call it GVTG, Intel Graphics Virtualization Technology or something, and there they have a device model internal, which is kind of interesting. So you don't need to implement your own, graphics device model. Okay, some references for if you want to look it up online. And it's demo time, I think. Okay. All right. So this is a real old demo here. Used it a lot. So let's see what that's some standard Mesa demo stuff. And to see that we can have two, there would be our gears. So these would be two separated clients at this time. And we did some more sophisticated things. So we ported a shader from ShaderToy, like one-to-one. We'll see if it lives. So and this is rendered, compiled at, you have the shaders compiled in the machine code, load on the GPU and execute it. So and that would be 3, yes. So let's see if we can do 4. Yes. Just because you can. All right, that's it. Yeah. Okay, the question is if we have some priority handling. We haven't implemented that, but it's, I mean, you kind of schedule context, can implement something like this, yeah. It's not a problem. I mean, you can say what you're executing next in the driver. So you can have any policy you have. Yeah, you kind of can. I mean, you can reset the car, and they say there is some notion of preemption, but we haven't really found that yet. But the question was if you can stop rendered work, if it's all rendering, right? Yeah. Okay. Yeah.
I understand correctly, you have modified Mesa library on writing new backend.
We wrote a backend for the EGL.
So did you try to submit it?
Did we have modified the Mesa library?
Did you try to modify at least some changes upstream?
No, because it's too. So we didn't have some changes upstream because it's too old by now. So we ported 11.2, and since then we are now at 17 or something. They changed the versioning. Yeah, we just have a new EGL backend, and we changed the DRM backend. But DRM is not Mesa.
So my question is mainly whether it's somehow possible to communicate with the Linux graphics community, whether they are open to these activities like what you are doing, or it's...
So the question is if we could communicate to the Linux community. Yeah, maybe. Maybe, yeah. So, but you know, the Linux community is so big, and Intel has how many people? 150 in open source. So they are doing their things, and until now we were the small guys. So I don't know. We could try. Yeah.
Am I right that the output of the GPG image is copied to the frame buffer?
The question is if the output of the graphics card is copied to the frame buffer, right?
So is it still puts a strain on the CPU to just do the copying of the image to the frame buffer? Is it possible to use the GPU for that too?
So he asked if it's possible to use the GPU for pixel copying, and yes, we use the Blitter engine. That's what it's there for, and we want to use that in the future. But it was out of scope of this kind of work. And I mean, you can copy with 3 gigabytes per second on a modern CPU, so it's sufficient. Okay, more questions? Yeah.
Do you have some project for this? I mean, did you do this for just showing that the G-Node can do this, or do you have some business in mind?
So do we have some project for this? Yes. So we want to use G-Node on a daily basis. We use it on a daily basis, and we want to have 3D acceleration, right? Mm-hmm. So it's going to be integrated into the main G-Node, our scenarios someday. Hopefully pretty soon. And the other thing is we want to look into this graphic cards virtualization thing, and it would be cool to have like a virtual Linux or what, which could take advantage of 3D somehow. And all the approaches right now, up until now, are not really good. Yeah.
Are you looking to another GPU course?
So are we looking into other GPU cores? Yeah, we could look into AMD. There is documentation there. NVIDIA, of course, is a no-go because, you know, Nouveau and all this thing. Yeah, but it's, I mean, this took like too many years to do. So you don't do it like every day. And you don't do it without funding, you know. It's a little bit hard for fun. Yeah.
Yeah, if I can maybe briefly speak to the last point, because you had a question, and I actually work for AMD on our graphics drivers. So the Mesa part, I think you can just take one-on-one like you did for Intel, and that's the right way to go. For the kernel stuff, multiplexer stuff, you really are biting off a lot of stuff, because these drivers are huge.
I know.
Trying to re-implement them is a pain. There are lots of people working on those, and if you can find any way of taking the code that's in the Linux kernel and maybe somehow adapting it, that would probably be the way to go. I know it's not the microkernel philosophy, but...
So the guy from AMD said it's hard to get the kernel part working. He said the user part is fine. And what we should do is like try to port the kernel part. So guess what we did with the Intel driver first? No, we did it. On this one we had Quake 3. Yeah, but yeah, that's a good side. Okay, I think that's it.